All right, greetings. This is the review for Physics 1101, Exam 2, on chapters 3, 4, and 5, even though part of 5 will be on the next test too, and I'll talk about that later. Test will be approximately 17 multiple choice questions and 5 short answer problems. All right. All right, you'll again have approximately 100 minutes to do it and one attempt. So, all right, so that's the test. I'll go over some of the chapters, sections here for the cover and some of the basic questions. So that's the basic test right there for exam 2. So, all right, so moving on. For chapter 3, and again for chapter 3, that's dealing with two-dimensional motion, but we are using the equations from chapter 2. Again, in the horizontal direction, acceleration is just whatever it is, like a car, but there's no acceleration due to gravity. So this is the case here. I mean, depending on a car accelerating, A is just given, either given to you or calculated by how far it travels. So again, this is the x direction. These are equations from chapter 2. In the vertical direction, which we talked about in chapter 2, then acceleration is always g, which is minus 10 meters per second squared, or minus 9.8 meters per second squared to be precise. So this is up is positive, but since gravity pulls downward, it's negative in the case of where we need to have a vector. All right, so we did this in chapter 2, x direction, y direction separately. In chapter 3, we're combining the two to analyze problems that way, and we've talked about that already. So I'll leave that up for a minute. As far as that's concerned, all right? So as we move on, before I get to that, section 3.1, vectors, graphical addition, and that's using that PHET program, PHET, which adds vectors. And if you have a vector too, right, this is the x direction, y direction. If we have a vector like this, and then a vector b, so this is A, this is B, tail to head, the result is this, C. So the result will be the length is R, and the angle is always with the horizontal. So it'll be positive, so positive angle would be like that, negative angle would be this way. So negative angle relative to the x-axis, so a negative 45 would be down here. All right, if you have two vectors that are such like adding A and B this way, right, again, this won't work. The result would not be across like that because you have to add tail to head, tail to head, tail to head. So we would slide B up to here, keeping in mind that the result, this is the same as that because the direction is the same side. So that would be C. Right? And using the FET program or any other way you want to do it, that would be the result. So you can do this using a protractor easily too. You can do the component method. I'm not getting to that at all. The component method is described in section 3.4. As far as that's concerned. The only thing I didn't really touch much about is that if I have a vector B like this, then minus B is that way. It's just the opposite direction. If it's like this, is A, then minus A is just turns around the other direction. Okay, so I'll leave that up there. Have you look at that a little bit. And this would be true, as I should add, if you had more vectors. If you added a vector D here, then the tail to head, tail to head, tail to head, this would be a result of all those. Right? If we added A plus B plus D as vectors, we'd end up to C. The little line over top means the vector, and that's how you would do it graphically, depending how many you had there. All right. So that is section 3.1, and really up through 3.4. 3.4 is the component method of adding vectors, which we're not getting into. Very long, complicated section. It uses sine and cosine and trigonometry. It's a method you would use for complicated problems, engineering problems, but for this class, we're not doing that. All right, so that's vectors. I'll move on here now to the next part. And next section is 3.5, and this is projectile motion. Again, taking the sections from the book. If you have the PowerPoint lectures, that's fine because I'm going to show the equations anyway. There's two cases we're going to be dealing with here. And I will, in this section, and this is also 3.6, so I might as well just combine them together. All right, the type of projectile motion we're going to have is where you launch something and it comes back to the same height, drops back at the same height. So like kicking a ball off the ground and it travels this distance r with the speed, velocity or speed v and an angle v naught, I should say, at an angle theta. In this case, where it lands at the same point, the range r is given by v naught squared over v naught squared times sine of 2 theta over g. Down right. Yep. All right. So it's a sine, twice the angle, the sine of that. So keep that in mind. Don't forget that. Right? And then this is the speed in that case. So we've done some examples. Again, we used some problems with the FET program to solve this, where g would be 9.8 meters per second squared to be precise. The next part, as far as section 3.5 and 3.6 is concerned, is if we have projectile motion of an object being thrown off a cliff, a certain height y, and it falls out a distance x. Right, we talked about that. And the fact that this is parabolic motion. Like the example in the book, what they have is you have a ball is dropped and another one at the exact same time is shot horizontally. They'll both land at exactly the same time because of the fact that this direction motion this way has nothing to do with the motion this way. So in this case, that's part of the examples I talked about here. The relationship between distance and velocity is velocity will be distance traveled horizontally over the time it takes for it to fall to the ground. All right. So we have problems that way. Either you're finding how far out it goes at a certain speed, how long it takes, or how far it falls, given how far out it travels. So you're going to be given generally 2 out of the 3 here, either distance or y, velocity or x, or velocity and time, and problems related to that from chapter 3.6. Right, so those are the only 2 kind of cases we'll be dealing with for projectile motion. All right, and that's all of chapter 3 is concerned. Okay. All right. Now, as the so that's chapter 3. I'll move into chapter 4. Actually, before I remember, let me emphasize one thing here in chapter 3. Is I want to make sure I'm clear on this. If it's launched at a horizontal velocity v, travels a distance x, falls a distance y. Since gravity is only acting this way, where a is g, which is minus 10 meters per second squared for problems, in the x direction, relationship is v is x over t. So x is velocity times t. This is constant velocity. In the horizontal direction, this is only in the x direction. In the horizontal direction, the initial velocity is 0, so y is given by 1/2 gt squared. So the distance it falls is 1/2 gt squares. So if you know the time and velocity, you can find x, and you can find how far it falls based on this. So that's the only thing I want to add for chapter 3 is that part. Okay. So that's chapter 3. I'll move on to chapter 4. And for here, all right, this is chapter 4 is Newton's laws of motion. All right. First law, moment of inertia. First object moves at a constant velocity unless the force acts on it. Second law, F equals ma. Well, this is in newtons, this is in kilograms, this is in meters per second squared. And third, as we've talked about already, is action, reaction, and this is described clearly, first section of chapter 4. In space shuttle, you shoot out exhaust as fast as you can. That way, the reaction is to push the shuttle itself in the other direction. So that's Newton's laws of motion, as far as that's concerned. We did problems with this equation. And such. And let me right. And we did with this cases of F equals MA. We have the Atwood machine. M2, and the fact that the relationship, the force is going to be G times M1 minus M2. Because the force, they're both counteracting each other, but the mass being accelerated are both of them together because they're attached. So this is the Atwood machine we talked about already. And then we had the case of an elevator. All right, what is person inside the elevator? What force would they feel if you're accelerating upwards? So A is positive, or if you're accelerating downwards, A is minus. Okay, how do you feel inside the, what is your weight that you feel like inside an elevator? Is either accelerating up or down, or moving at just that constant velocity? So that's part of section 4.7. All right, the last section here on 4.8 is dealing with so this is section 4.7. 4.8 deals with 4.8 deals with friction. And in this case, frictional force is mu times your weight, where force of weight is m times g. So mu is a constant, again we talked about, and there's different kinds. You got mu static and mu kinetic. All right, and comparing the two and the fact that mu static is always greater than mu kinetic. So that's chapter 4 as far as those kind of problems. Okay. And if you need to calculate this, either we'll provide it in the problem itself, or if you need to calculate mu, remember mu varies generally between 0 and 1, where 0 is no friction at all, and 1 is frictional force equal to the weight of itself. All right, so that's chapter 4 is concerned. All right, last section I'll deal with here is section 5, the beginning part of that, and this deals with circular motion and gravitational motion. So I'll leave that for a minute before I start chapter 5. So chapter 5, most of this will be doing on circular motion. And a little bit on gravitation, but we'll be doing more on the next test of this part. So the reason they're connected is that when something is moving in a circle, we talked about this already, radius r, and velocity v. The centripetal acceleration is given by v squared over r, where this will be in meters per second squared. So this is centripetal acceleration. The reason this connects with gravity is that gravity, which eventually was solved by Newton's law of gravitation, is that gravity is pulling downwards on an object, so force of gravity. So what happens is, for an object to stay in motion, it has to do a circular orbit. If you just throw a satellite straight up, it'll just crash back down. But to keep it in orbit, you have to have it, give it a certain speed so that this gravitational force is balanced by the centripetal force, mv squared over r. Or in this case, for something orbiting Earth, this is this r is the distance from the center of the Earth. Now, the center of the Earth is around 6,400 kilometers. So this is how we end up with G by balancing gravitational force with centripetal force. So since gravity is rather strong, for an object to stay in speed, if it's near Earth's surface, it needs to travel on the order of about 17,000 miles per hour to actually stay in orbit. So when you actually launch a rocket, it actually is, most of the energy is actually put into giving it a horizontal speed. That's why they launch rockets at Cape Canaveral in an easterly direction, because you get the Earth's actual rotation to help with it. So they're going about 17,000 miles per hour. If you ever seen the movie Gravity, with Clooney, George Clooney, and I can't remember what else is in it. Anyway, that they have, objects going at a high rate of speed, which eventually cause certain things to collide. That's part of the dangers of space. So for an orbit to go that fast when it's near surface, but it only takes about 90 minutes to orbit. So things near the Earth's surface only take about 90 minutes to orbit, like space station, space shuttle, most satellites near the Earth's orbit. While we're still on this, I'll do one last thing for here. However, on the other hand, if you have dish network or any kind of satellite system, those things stay at one spot over the Earth's equator, and the only way it can stay at one spot is this what we call geosynchronous. I'll put it up here. Geosynchronous orbit. And that takes 24 hours. And because of that, the satellite stays in one spot orbiting exactly over the same spot. But to be this far away, to do this, this has to be a distance of about 24,000 miles, or about 40,000 kilometers above the Earth. So it's way out here. All right, so the farther out you go, the slower they do. Now we go out as far as the moon, and the moon, the moon takes 29 days. All right, so that's the range we have here. At the Earth's surface, it takes about 90 minutes. At geosynchronous, it takes 24 hours. Now obviously this is the scale. But for the moon, which is way, way out there, 240,000 miles, it takes 29 days. So that's the only part of Newton's law of gravitation that we'll be covering for this exam. And as we keep in mind, the mass of the object has nothing to do with it. It only has to do with the speed it is going and how far it is away from the Earth's center. The same thing here. The centripetal acceleration depends nothing on the mass. So two things can be two objects in orbit, one very light, one very heavy, can be in a circular orbit, has nothing to do with the mass of the object. So that's that part there. The only other part I want to cover here, and I'll leave this up for a minute, is that, all right, what's the other part we want to cover? All right, the only other thing I want to do is frictional force, because for orbit, gravity balances centripetal force on a surface, on the car, say a car traveling in a circle. Well, let's not do it that way. Let's say it's going straight, and then it hits a turn. I talked about this already. So it has some speed, and it enters a turn of radius r, with, depending on the condition, whether it's mu, again, ranging from 0 to 1. If it's 0, that means like glare ice. If it's 1, it's like a very hard road. All right, so V over R, so centripetal force is trying to pull it outwards, and that's mv squared over r, where this is the speed in meters per second. This is the radius in r. What's pulling it inwards, as we've talked about earlier, is the frictional force given by mu mg. And as we talked about, as long as this frictional force is greater than that, it'll stay on the road. If this number is greater than that, meaning that frictional force is greater than Fc, or mu mg is greater than mv squared over r. Notice the m's cancel out. As long as that's greater, it'll stay on the road. If this becomes, the maximum it can be is when they're equal. So the maximum is when it's equal, and if this becomes greater than that, then it'll go flying off the road. And so some of the problems relate to how fast can you go into a turn, given what the road conditions are, and will you make the turn or not make the turn, depending on what they are, depending how fast you're going, depending on the radius curve. So we've already covered part of this, and that is basically all of chapter 5 that we're going to be covering here. We'll do some more problems on Newton's law of motion in the next test, but that's the extent of chapter 5 for test 2. So here's your expression. Again, centripetal force is that way, frictional force is that way. All right? Okay, so that's test 2, which starts in a couple days. And again, I've talked about what it'll be.